So, welcome everybody. Is it possible to call native functions directly from Java without using any C or anything else? Well, I guess we have a clue up here in the headlines. I'm going to talk about function and memory access in pure Java. My name is Per. There is my social handle, and I work in the Java core library team at Oracle. And here is the agenda. So we want to talk about something called foreign function and memory API, which I'm going to call from this point on FFM, or the FFM API. And that is basically two parts. One part working with memory, and the other part is like invoking native function. And after that, I'm going to talk a little bit about the tool we have that can make automatic binding of C libraries, so we can get all those foreign functions written for us automatically. That tool is called jextract. We're going to do some live coding. And then I'm going to talk about the evolution of the FFM API. We have shipped it, but there is more to come. And then a short summary, and then hopefully I will hear your reactions and questions if we have time left. So, the FFM API was shipped in Java 22. It was finalized there, thanks to Maurizio and Jorn's relentless work during a number of years. And finally, we were able to ship it. And if you read, this is the book I have, my book of effective Java, and there you can read, use native methods judiciously. And I think you can see at the bottom there, it's rarely advisable to use native methods. And maybe that has changed a bit since that book was printed. So there is a lot of native libraries out there. We have like off-CPU computing libraries. We have machine learnings like ONX. We have graphics processing libraries. And these libraries are not written in Java and will not be written in Java and should not be written in Java. But still, we want to leverage them. So how can we do that in a good way? Up until now, or rather up until recently, the only way to do that was basically through JNI, which is a Java native interface. And the JNI allows us to access functionality that's not in the JDK. So what you do is that you declare one or several methods as a native method, and they don't have a body. It's kind of an abstract method. And then run some code, and then you can write the implementation of that method in C, C++, or perhaps even assembly. And I've seen horrible implementations of such functions. And there are a lot of problems with this. We have this kind of native first programming model. So this kind of brittle combination between C and Java, which has different models and different programming models. And it becomes very expensive to maintain and deploy. We are seeing this in the JDK itself because we have a lot of native methods there. And it's kind of cumbersome to pass data to and from JNI, and you have to kind of do this transition from Java to native code. So there is something missing there, obviously. This is how it works. So you have a Java client, your code there, and then there is a glue in between, which is JNI, and then the JNI calls this native library. So if you look into the details, we have this native methods here. You invoke command javac.h -h, and then that creates a header for you, which you then implement, and then you have to compile that to a shim DLL, which you then have to load. So it looks like this. You have a Java class, you load this shim library, which is not there yet, and then you declare this native method. And once you run this javac-h, you get this kind of a.h file that you are supposed to implement. And here is such an implementation. And as you can tell here, there are a lot of parameters that are not used. We just invoke the getPid system call here. So it's just a wrapper around the system call. And as you can see here, it's quite cluttery. So there must be a better way. And that was about JNI with calling the actual function, but you also often need to pass data to your native calls. And JNI only supports like primitive types and Java objects. So the way you can work with memory up until now was that you used direct buffers. So you allocated the direct buffer, and then you can send that to your native code. And there were some utility methods there that allows you to work with direct buffers using C, converting to pointers and things like that. So there were a lot of problems with the direct buffers. So there is no way to deterministically free or unmap such direct buffers. So you create them, and they are there, and hopefully sometimes they will get garbage collected. They were also limiting addressing space. When we first wrote the direct buffers, we thought that, well, 31 bits, that's a lot of memory. It's like almost 2 gigabytes, so that should do. But as memory grew, that was no longer the case. And also, like direct buffers, they have this kind of inflexible addressing options. You can either use them sequentially, because a byte buffer has this kind of cursor that's maintained over time. And so also the direct buffer was immutable, which is not that great. So there are also many frameworks that is kind of trying to release the pains of JNI. I won't mention them here, but they are not the answer. At least we didn't think they were the answer to the more bigger questions, what we were looking for. They were often fractured, they relied on unsafe, and it made deployment even more difficult to do. And what if a client only needs working with memory? Maybe I don't want to invoke a native method. Maybe I just want to work with flat memory in a good way. Maybe I will memory map a terabyte, and then I'd like to work with that in a good way. So it was apparent we needed a kind of more Java-centric programming model. So we can replace JNI, and we can replace the direct buffers with a much more efficient and future-proof API. And then we also like some ways to simplify the building of native bindings. So that's what we did in the foreign function and memory API. And now I'm going to talk about the memory part. How do we work with flat memory? So accessing flat memory is made through something called memory segment. How many of you have actually worked with memory segments in the FFM API? Very few. Great, then you are at the right talk. So now you're going to learn more about this. So a memory segment accesses a 64 region of continuous memory. And there are two types of memory segments. There is a heap segment, which can be backed by an array, for example, or also some other heap constructs. And there are native segments, which are native memory outside the Java heap, that you can typically get by invoking the native methods malloc or mmap. And a heap segment can move, because a garbage collector can move heap objects, whereas a native segment always remains stationary and is not touched by the GC. Okay. Oh, there's something wrong here. Let's see what we missed. Okay. So how do we access a memory segment, and how is that guarded? So a memory segment has a certain size, so it's not possible to address the memory segment outside its size. So no out-of-boundary access. It's also governed by something called a lifetime. So when the lifetime ends, you cannot access the memory segment. And there is an optional confinement that you can elect to impose on your memory segment. You can say that this segment is constrained to this particular thread, namely the thread that firstly allocated the memory segment. And that prevents data races, and you cannot accidentally share this segment with another thread and create like visibility or other thread problems. So here is an example. So let's say I have a C struct much like this. There is a double with the name x, another double with the name y, and then I instantiate a point with the sides 3 and 4. So don't worry about this arena stuff right now. I'm going to talk more about that later. But here I allocate two doubles. A double is 8 bytes, and there are 2 of them, so therefore 8 times 2. And then I can set a double value at index 0 to 3, and set another double value at index 8 to 4. So that is kind of a mechanical way to use a memory segment. It's quite primitive. We will see we can do it much better later on. And so if I'm trying to access outside the bounds here, well, it's going to blow up in a deterministic way. I'm going to get an index out of bounds exception, like this. So that is good. Oh, I don't know what's wrong here. No? Okay, so we have no out-of-bounds access. We have automatic deallocation, which is not good. We wanted to have deterministic deallocation, and we are doing all this kind of manual offset computation, which is not very good, but we are going to fix that. So talking about garbage collector, I think the garbage collector was a very good thing. That was one of the reasons Java became so popular. So when you create a new object, the GC can recycle that object, and it hinges on the concept of reachability. So when an object is not reachable anymore, it's editable for collection. And that is one of the cornerstones of Java's success. And direct buffers, they relied on garbage collection. But there was an issue. A direct buffer might be very small in terms of just looking at how many bytes the actual object constitutes. But it might hold a reference to like a gigabyte of memory. And so it's kind of tricky to kind of find these and prioritize the cleaning up of them. And it's also relatively expensive to traverse all the reachability graphs, and especially if you have a very large heap or if you have a kind of low latency collectors, because every time you look at the heap, you are kind of polluting the cache in your CPU. So the GC cannot track usage of off-heap resources. So that was a challenge to provide a deterministic way to deallocate stuff in a language that's actually built on automatic memory management, which wasn't easy. Okay, so what's the problem with this? So one problem is that you free memory too early, and of course that is not good. So that is use after free. And another problem is that you might not ever free it, and then you create a memory leak. So that is the kind of two outliers that you want to avoid. So we have like C's, malloc, and free is kind of two level. How many of you have coded in C? That's pretty much so. And please keep your hand up. And if you have ever experienced a problem with addressing outside a pointer arithmetics, or used a memory segment that is free, now lower your hand. There are no liars here. Great. Okay, so when you do it in C, every allocation is a fresh lifetime. You allocate something there, and they are not related. And pointers can be freed at any time. In fact, you can have a pointer on the stack as well. Okay, and then we have Rust, which is kind of on the other side, has ownerships and borrowed built into the language. And the programming model can be quite inflexible when it comes to like cyclic data structures. So and before I go into that, here is an image showing the problems with use after free and memory leakage. So the solid ones are the ones that are live, and the gray out are the ones that have been freed or marked for deletion. And A here points to B, but B is free. So this constitutes, on the left-hand side, a use after free case. And on the right-hand side, it's like, I've freed C, but it still points to something that is live, so that is a memory leak. So what we wanted to end up with was this kind of balance between flexibility and safety. And the way we did that was to introduce a concept called arena. So an arena models a life cycle of one, or importantly, more segments. So you can have an arena, and you can allocate several segments, and they are all in the same life cycle. So they share the same life cycle. And all arenas provide safety guarantees. So there are no use of the free, and the close operation of an arena is an atomic operation. So if you have 100 segments, they are all atomically closed when you close the arena. Okay, and we ship several arenas in the FFM API from the beginning, providing out-of-the-box functionality. There is a delay here, so that's okay. So here are the arenas. There is a global arena called which is unbound. The global arena is created when you start the JVM, and it will remain there until the JVM closes. So it's never going to be closed. And every segment allocated there will remain forever unless you take special responsibility for it. We briefly saw this automatic arena, which emulates a garbage collection so that you can use a memory segment the same way as a direct buffer. And you can say that when this is no longer reachable, the memory segments are cleaned up for you automatically. That is sometimes usable, but it's not like deterministic. And the two ones almost at the bottom are a confined one, which you have to close yourself. If you don't close it, the segments will be there forever, but you can yourself decide when you want to close it and all the segments that is allocated. And the confined arena is confined to the thread that's allocated them. And then there is the shared arena, which is the same as a confined. You can close it, but then any thread can use it. And there is a kind of price you pay for that, because when you close the shared arena, it invokes something called a thread local handshake, which makes sure that there is no other thread in a critical session using any of those memory segments. So it takes a little bit longer to close such an arena. And then, of course, you can roll your own arenas. Arena is an interface, and you can implement your own arenas. Maybe you want an arena that just logs whatever is being allocated or who is allocating it. Maybe you have a memory map file from which you allocate memory, or maybe you want to reuse memory. So you can roll your own arenas. So I think we ended up in a good place, striking the balance between Rust and C. Okay. Now armed with the arena, we can go about and do this much better. So we create an arena, and arena implements the auto-closable interface, so you can have it in a try with resource block. So we open up a new arena here, and then we allocate 16 bytes, and we set the value. And when we enter the block, when we exit the block, the arena is closed for us, and the memory segment is deallocated deterministically. And if I'm trying to leak this point here, which I'm doing with this kind of hack, and if I'm going to try to access that, it's going to throw an exception like this, illegal state exception, already closed. So that it's not possible to use segments after the corresponding arena has been closed. So it's getting better. Now we have deterministic deallocation, we have no out-of-bounds access, and no use after free. But you still have this kind of annoying manual offset computation. So we're going to take a look at something called memory layouts. So often memory layouts occur in a structured fashion. We have like point.y or point.x. And as you saw, it's kind of not so very structured to use manual computation. Maybe you add a field, or maybe you move fields around. So there is a way to describe memory layouts programmatically. And layouts can be queried to use the size, alignments, name, and access expression. So this leads to more declarative code and less places for bugs to hide. So if we look at the memory layout hierarchy, this is from the Java docs, and here you can see the permitted implementation of memory layout. So there's something up there called a sequence layout, which corresponds to an array. So you can have a sequence layout of other layouts, and maybe you have 10 or 23 of them, elements. And then there is something called group layout, which can be a struct or a union, which all of you who raised your hand, having used C, you know what that means. You can have padding, which is unused or reserved area. And then there is something called value layout, which kind of reflects the primitive types, like bytes and longs and double, which you saw before, and even addressing. So let's go back to our example with struct. So here I have a struct point 2D, and this is the way I can model that in Java. So I have a struct layout, and I have a double with the name of x, which corresponds to the above. I have a double with the name y, which corresponds to the above. So it's very easy to kind of convert C structs to Java structs. And a value layout, like double, has several ingredients. It has like it has a carrier type, in this case double dot class. It has an endianness, because on different platforms there are different endianness. There are little endians or big endians. And even though you might run on a little endian machine like mine, Mac is a little endian machine, you might want to work with big endian, because that's a network order. And that can be automatically handled for you if you just set the correct endianness. And there is alignment constraints. This becomes important on certain platforms when you do atomic operations, for example. So a value alert can be used to query. So you can query for a var handle. And a var handle accepts a memory segment and a long coordinate. The memory segment itself is where you want to access this, and the offset is within that memory segment, where do I start? And you can obtain var handles from nested layouts just by querying. I want the var handle for this kind of path. And using var handles as access mechanism has many advantages. So there is support for fenced atomic operation, for example, compare and set operations and increment atomically. And there is a lot of optimization for var handles in the JIT compiler as it is. And there is also a rich combinator API. So you can take a var handle and you can say that I want to plug in always a parameter for this parameter for 0 or something else, and you can build up your own kind of var and method handles using that kind of combinators API. So here is an example. We have our point. We have our layout. Still delays. And then I can ask for the var handle for X. So I'm saying that within this layout, I want to have the var handle for the group layout named X. And that is, of course, the first one. And then the Y handle is the same, but for the Y component. And these var handlers now will know the offset within this struct layout. So the kind of inherent offset for X is 0, and the inherent offset for Y is 8. And then I don't need to care about that. I can just use the handles like this. So I use the X handle set in this point, and the offset is like a general offset, so they are always 0 in this example. And I set it to 3, and Y knows that I should offset by 8, so I set that to 4. So now we have deterministic deallocation, no out-of-bound access, no use after free, and offset derived directly from layouts. So imagine, for example, that I swap these around and have Y before X, and then my code would still work. Okay, so that was memory. Now let's look at the functions. So let's assume we have an external function called distance that computes the distance from a point to the origin. And the way I do that is that I have a lookup. So this is kind of a symbol. So I say that I use this loader lookup and find the symbol distance, presuming now that I have loaded this library in advance. And once I have found this lookup, I can invoke a method in the linker called down call handle. A down call is when you go from Java to native, and up call is when you go from native to Java, because Java is always at the top, isn't it? Okay, so we say that we have the down call handle with this symbol, and then we have a functional descriptor. And the functional descriptor said what is the return type and what are the parameters. Because the down call handle needs to know the platform that we are operating in. Maybe it's Windows, maybe it's Mac, maybe it's Linux, or maybe it's AR64 or X64. They all have different calling conventions, so we have to put the right parameters in the right registers or put them on the stack, and only then invoke the method. So that is something that's derived from the function description. And once I have this one, the method handle, which encapsulates all this, then I can set my values, and then I just invoke this method. And because 3 to the square plus 4 to the square, and the square root of that is 5, and presumably that is what I'm going to get back from this native call. And I think here we have the answer to my initial question: is it possible to invoke a native method directly from Java? And the answer was, unsurprisingly, yes. So I will take a deeper look at that in the live code session shortly. And the performance is good. It's about the same performance as JNI when you do like this. And there is kind of a trick. You can say that this method is trivial, and that means that it will take a very short time. Then we can shove up some additional times, like if you want to get the PID or if you want to read a clock. That's a very short operation. Then it's even faster. So that brings us to the next section, which is the jextract, which can automatically create these kind of bindings for you directly from a .h file. So jextract is a tool that for now you have to download it. It's not included in the JDK itself, but it's easy to download. And then you can say that I want to inspect this .h file here called studlib.h and generate bindings for that automatically. And then, as I said, it will be in org studlib. I can just statically import that, and then I can use C code directly from Java without having to write all these bindings automatically. So here is an example when I call qsort, which is a standard library function. I'm a bit careful here because it's like lagging. OK, so I create the arena. I have an array which is not sorted. Then I use the method called allocate here, which has been generated by jextract, which is used to allocate a callback. So I can call back directly from native code into Java. And here I just, and what I get here is two addresses, address 1 and address 2. And so I view the contents of them as an integer and compare them. And then I invoke the qsort method. And say that I have the array, which is a pointer to the array. I have 10 elements, and the size of each element is 4. And here is my comparison method. Here's how I compare them. And every time qsort runs, it will call back to Java to determine which of these two elements are the largest. And then we will end up with a sorted array. So this shows an up call. And the good thing here is that up call is much faster than JNI. Because Jorn has put in a lot of effort and optimized this. So you will see a significant improvement if you have upcalls from JNI and convert to FFM. So here's the way to download jextract. You can take a photo of this, or you can go to jdk.java.net and download it. And in jextract, there are a lot of examples, like OpenGL, you have TensorFlow, libffmpeg if you want to convert videos from Java. And it's very easy, actually, to use these native libraries. You don't have to wait for someone to write the bindings for you. You can just maybe download it, use it your package manager, and then you can use jextract, and off you go.
Is there a payment plugin for this?
I think so, yes. Someone wrote that. So I'm going to do some live coding, and hopefully this will work. So I'm going to head over here. Hopefully you can see this. So I prepared for a question I almost always get when I talk about the FFM. Is it possible to model like NumPy, where you have dense matrices of doubles or ints and things like that? And the answer is, of course, yes. Otherwise, I wouldn't have talked about it here. But here I model a float matrix 3 times 4. So I say I have a sequence layout with 3 elements in the first dimension. And I have another sequence layout of 4 elements of Java floats. So here I can model a dense array, which is 2-dimensional. And if I print that, this byte size of that, hopefully that will give us 3 times 4 and times 4, because the size of Java float is 4. And then I can query this layout for a var handle. And in this case, I'm using a special query called sequence element, which means I don't want to give you a specific index here. I want a general case. So the sequence element will add an arity to my accessor. And I do the same for the Y component. So hopefully I will get something called memory segment long, which I always get. And then we'll get from this sequence element 2 extra coordinates here that allows me to specify X and Y for this layout. And here is quite a small example. I allocate, so now I can provide my memory layout, not actual size, but I can say that here's my float matrix description, and I want to allocate a memory segment that has this particular size, but also this alignment constraints that the float matrix has. And that will be taken care for us automatically. And then I just set some random component, 2.3 to 42, and then I read it back, and hopefully that will provide E equals 42. And if I'm trying to access outside bounds here, the value, the var handle that's been returned to me also checks each and individual index for me, so it's not possible to use individual outside of index. So I'm going to run this here. NumPy. I got an exception, which is in this case good. So the float matrix size was 48, just as we hoped. We had a var handle that takes a memory segment, a general offset, and then the 2 coordinates for x and y. I did actually read out the E as 42, and then I got an exception saying index 100. It's also bounds for length 3, which is just what I wanted to see. So that's that. That's the only thing I'm going to say about memory layouts. So now I'm going to talk more about invoking native methods. And if you remember my kind of brittle example with PID in the beginning with all the JNI code, I've done exactly the same here with pure Java. And as you can tell, it's a much more cleaner solution. I get a native linker. I say that I want to get the symbol for getPID, which is part of the system libraries. And then I ask for a downcall handle, and I'm saying that this PID doesn't take any parameters. It only returns a Java int. So if I print this, I'm going to have a method handle that doesn't take any parameters, but it returns an int. And then I invoke this method handle and print the PID. And hopefully that will work, so let's try that. So this is the one. I'm running that, and it says like PID equals 84,000 something. I'm going to run it again, so hopefully we get something else. And yes, we did. So it appears to work. And that is great. Whoa, Mac OS update. I don't want to do that now. OK. But it can be even better. So I put together this very small utility method where I provide a name, where I provide a functional description. But as a top of that, I provide something called a type here. Now, the type, this is a trick I'm going to teach you. So the type here is a functional interface. A functional interface only has one abstract method. And it's actually possible to return something that implements that interface, and that will use the method handler I got before under the hood. And I will use kind of pure Java semantics. I don't have to invoke all these method handlers and all that stuff. So what I do is that I look up this symbol, just like before. I ask for a downcall handle, just as before with the descriptor. But then I invoke this kind of semi-secret method called method handle proxy as interface instance. And this is the glue between my method handle here and the implementation of this type that I provided. I provide a class literal, and I will get an implementation of that. And it's going to be apparent to you why this is good in this second example. So if we look at the PID function, it actually conforms to something we already had, an int supplier. An int supplier has no parameter, but returns an int. So I can reuse that. I don't have to define my own functional interface here. And I say that I want something that is an int supplier. And I'm going to invoke the getPID function, and here's the functional description. And if you squint a little bit, you can see that it's actually not even required to provide a functional descriptor. I was just lazy. But it's possible to write such a utility method that will use reflection on this and figure out what is the only abstract method and see what are the parameters, what is the return type, and figure out the functional descriptor automatically for you. But I was just lazy, but maybe you can do that. And then I just invoke this PID here. So this becomes now very short and kind of Java-like. So let's run that. Boom, and it actually worked. So I think this is a good way of kind of hiding native bindings and kind of exposing them to your Java code or maybe your clients, that if you're a third-party developer. And time is kind of short here, but here's another example where I have something called a dispatch. So I have the method I had before, and I also want to kind of create a dispatcher that has the string length method. The string length method is also a native method that takes an address and returns a long, and it says how long is a C string. So I said I have an interface that have this kind of two function, and then I'm using a trick. I'm using a record here because components in a record are trusted by the VM. They can never be changed. You can't do set accessible true to a record component, and you can't discover the offset using unsafe, for example. And so they are trusted by the VM, and that unlocks kind of performance gains. So I just provide the PID function, I provide the string length function, and then I just delegate it to those functions here when I implement the function. And of course, when I create this dispatcher here, I just provide a same code that we did before and a similar code for the string length function here. Now the string length actually takes a parameter, which is an address, and it returns along. So here's how I can use them. I use PID, and I get the PID, and then I have I convert a Java string to a C string using this allocate from method, and then I invoke the system string length method, and hopefully we will see the correct string length here. And let me just do that before we continue with the presentation. So what dispatcher? I think a dispatcher. So let's run it here. And it sets the PID is this, and the length of the text Java1 exclamation mark is indeed 8. So that is good news. Okay. So that was the live coding session. So what about evolution? What are we working with? We are working with performance. So we are trying to improve the startup time. Now the startup time is the time before you start the application until it does its first useful work. We are also improving the warm-up time, which is the time it takes before when you start your application until you reach peak performance. Because as you can imagine, all those bindings is about spinning bytecode, and that takes some time to do. And we are working on improving throughput for all the FFM methods. And some of these improvements are actually available in JDK 27, so at 24. So we have improved the copying, mismatch, fill, and also the speed of actually allocating a memory segment in 24. And especially on ARM, it's a significant difference between JDK 24 and JDK 23. We are working on new arena types. There is an ongoing work that Ron is doing, but it's called structured concurrency. So maybe we will have some arena that corresponds to structured concurrency. Maybe we will have an arena that allows recycling, because invoking malloc and free comes with a certain cost. There is another effort called taming composite data. So as you saw before, you can query from method handles using all the primitives we have in Java, but maybe we want to define our own records, and maybe we want to use that as primitives. So that's another thing we are thinking about. Maybe we want to be able to call native function with records. And we are improving the jextract. We actually added support for macOS frameworks. We are about to use something called stable values, which is something that's going to preview in Java 25, and which I'm going to have a talk about in a few hours here in this very room, which can give a better startup time. And then we also have a JSON configuration file, which makes it much more easier to configure jextract. And maybe that opens up a path to a VS Code extension as well. Maybe someone will write that. Okay, so right now there are a lot of prominent libraries that are using the FFM API, and we are seeing maybe every week a new library picking this up. And in fact, this is something we are going to use ourselves. I think that is called eating your old dog food. So that is something we are doing. We are looking at reducing maintenance within the JDK itself. We are hoping to get better peak performance, but we are still having some challenges with respect to bootstrap and startup and warm-up. So we are working on that as well. And there is a nice connection between other efforts within the JDK community. We have Leiden, which will improve our startup times. We have the Vector API, and once that goes out of incubation, I think we can see better performance, even better performance for memory segment operations. We have Babylon, which is code reflection that allows us to use Java code and use the FFM API to maybe run that code on CPU of GPUs or AI-specific hardware. So, to sum things up, the FFM API provides a safe and efficient way to native memory. We have deterministic deallocation, layout API to enable structured access. We have general access to native function, 100% Java, no need to write and maintain native code. And there is a tool called jextract that automatically allows us to generate bindings for native code. And there is more to come. So please try out the FFM API today. Go and download the latest Java version and try it out with your app and see how much faster or how much nicer it will look. And with that, I'm opening up for questions. Or a round of applause. Okay. Anyone? Yes. Yes, please use the mic.
Is there a clear line in the sand between where you'd want to use jextract versus just kind of calling directly with the programmatic approach?
Can you repeat the question, please?
Sorry. Jextract seems like it can extract all the handles and objects that you need. Is there a way to do it directly without jextract? Like if you just want to call something in the C library, for example?
Yeah, so the question was, do you have to use jextract or can you use any other tool? And of course, you can roll your own kind of jextract thing, or you can write it manually, or maybe you can set up some kind of rule engine that will generate the bindings for you. Actually, it's not that super complicated to do it. So I guess the answer is yes, you can use other tools.
Thank you.
Well, thank you. Okay. Okay, that's another question coming up here.
You had an example of an array. Did I get it right that it's right now not possible to have an array of a struct, for example? Did I get that right, or is that a wrong conception from me, my side? Perception.
It's a lot of echo here, so I have difficulty to hear. Say again, please.
You had an example of a sort thing, you know, you sorted a quick sort, I think.
Yes.
You had an array of integers. And the question that I have is it possible to have an array of structures, like struct?
Okay, so the question was, in the example of qsort, I just have like primitive ints. Is it possible to have like a more composed structure, like structures of persons or structures of anything else? And the answer is yes, because qsort is very generic. So what you can do is that you will plug in a different comparator that knows that maybe my unit of data is not 4, but maybe 64, where I have my data, and the comparison is not like comparing two integers, but might be comparing the surname or something like that. So that is possible. Okay. Yes?
Thank you.
I assume checks, bounce checks, and the liveliness checks for the memory segments cost something compared to, let's say, unsafe. Is that, like, what's the cost?
Yeah, so the question is, what is the cost of safety? And I think, if I want to rant about it, the cost of safety is motivated, but I guess that's not what you're asking. You're asking, how much do we have to pay for this? And that depends, actually, on how you are using the segment. But it's like, I think now we're down to a few percent, maybe, and I think that is what you can actually expect. Usually we are able to hoist out checks. So you have like boundary checks can be hoisted, liveness checks can be hoisted by the JIT compiler. But there are still some areas that we need to improve in order to reach maybe the ultimate goal, which might be 2% off or something for unsafe.
Liveliness cost, how could it be hoisted? What happens if the other thread decides to free it? One thread is touching memory segment and the other thread is actually, let's say, force closing it.
Okay, so what happens if we have one thread that is using a memory segment and another thread is trying to change it or close it? That's the question. So there are safety guards built in here. So when someone is trying to close an arena, and then at next checkpoint, there will be a check that sees if there is any thread that is using any of these segments, and if yes, we're going to install a trap on that, and it's going to blow up. So it's not possible to kind of close and use after free, even though we are using different thread. And that's a quite tricky thing to do, because we don't want to do liveness check upon every access, because that will totally ruin performance. So therefore, for shared arenas, we have this kind of thing that's going on with the checkpoints.
Thank you.
Okay, one last question. I think we are.
This one's like, I don't know, maybe just a silly question, but all the examples you gave are using kind of standard C library things. But like QSort, would it ever be faster to actually do a QSort with like the standard library instead of just sorting in Java?
Yeah, I think given the cost for up calls, the answer is that no, it won't be faster using native calls. So this was more of an educational example. Okay, thank you guys. Thank you.